In this video we're going to look at how vectors can be used to obtain solutions to problems in mechanics. Before we start, it's quite important to just pick up on an important piece of vector notation. And the problem is that whereas when we write vectors, column vectors are a really convenient way of writing the vectors, when you're printing material for books or for documents, writing a vector requires two lines, which is rather wasteful in terms of space. And the way around this is that we define two important vectors, namely I, which is the vector 1, 0, or a step of 1 in the x direction, and j, which is the vector 0, 1, which is a step of 1 in the y direction. And then any vector can easily be written in terms of I and j. So for example, we can say that the vector 5, 3 is the same thing as the vector 5, 0 plus 0, 3, which is 5 times 1, 0 plus 3 times 0, 1. In other words, the vector 5, 3 can be written as 5i plus 3j. And similarly, the vector 7, minus 2 can be written as 7i minus 2j. When we're handwriting vectors, we make it clear that we are dealing with a vector by underlining, since we can't make our handwriting bold, which is the way that vectors are usually shown in typeface. So when we want to write the vector I, we'll do it as I underlined equals the vector 1, 0, j underlined equals the vector 0, 1. We've already observed the fact that the resultant of a system of forces is the single force that has the same effect as the system of forces, and that the resultant force can be found by calculating the sum of the vectors representing the forces. So, if we have a particle that is acted upon the three forces, F1, which is 5i plus 3j, F2 is 8i minus 5j, and F3 is 7i minus 6j, and we are being asked to find the resultant force acting on the particle, expressing your answer as a vector. Then all we need to do is say that the resultant force is the result of adding the vectors F1, F2 and F3. We know that F1 is the vector 5, 3. We know that F2 is the vector 8, minus 5. And F3 is the vector 7, minus 6. So when we add those three vectors up, the x components are 5, 8 and 7, which add up to 20. The y components are 3, minus 5, minus 6. So that is minus 8. And we can write the final answer as the vector 20 minus 8, or we could equally well write it as being 20i minus 8j. I would usually leave this answer as simply being the vector 20 minus 8. In example 2, the diagram shows three forces, F1, F2 and F3, acting at the origin. We're told that F1 has a magnitude of 8 newtons and makes an anticlockwise angle of 27 degrees with the positive x-axis. We've got to find the vector form for the force F1. We've seen how to do this in the past. We simply create a triangle, right-angled triangle, out of the vector F1. And we'll call the sides of that right-angle triangle, the x part being P and the y part being Q. Then using a little bit of trigonometry, we can say that P over 8 must equal cos 27. So P must be 8 times by cos 27, which is 7.128. And similarly, Q divided by 8 is going to be sine 27, so Q must be 3.632. That is 8 times sine 27. So the force F1 is the force, or is the vector, 7.128, 3.632. So we're now given that the vector F2 is the vector 1.8i minus 4.2j, and you can see that in the diagram I've now written that in vector format as just the vector 1.8 minus 4.2, and the vector F3 is the vector minus 3.7, 1.9. We've got to find the resultant force of these three forces and expressing our final answer as a magnitude and a direction. We know that to find the resultant force we just need to add up F1 plus F2 plus F3. So in that case, that's the vector 7.128, 3.632, added to the vector 1.8 minus 4.2, added to the vector minus 3.7, 1.9, which gives me the vector 5.228, 1.332. So we know that the resultant force has got an x component of 5.228 and a y component of 1.332, so we can draw a little picture of the resultant force. And using Pythagoras now, we can say that the magnitude of the resultant force, which is r, must be the square root of 5.228 squared plus 1.332 squared, which gives me 5.40 newtons. And we can find the direction of this resultant force by finding the angle theta. We've got tan theta is 1.332 divided by 5.228, so that gives me theta is 14.3 degrees. So we've got the resultant force has a magnitude of 5.4 newtons and makes an angle of 14.3 degrees to the positive x direction. For example 3, we've got the x and y axes lie on a smooth horizontal plane. A particle of mass 3 kilograms is acted upon by three forces. F1 is 5i plus 7j, F2 is minus 3i plus 5j, and F3 is k lots of I minus 3k lots of j, where k is a constant. We're given that the particle is accelerating in the x direction but has no acceleration in the y direction. We've got to find the acceleration and we've got to find the value of k. Well, Newton's second law tells me that the resultant force must equal the mass times the acceleration. And let's have a subscript x being the acceleration in the x direction. We know that there's no acceleration in the y direction, so that means that the vector for the acceleration will be the vector a subscript x as the x component and 0 as the y component. Newton's second law tells me that the resultant force must equal the mass times the acceleration. The resultant force acting is simply the result of adding the vectors F1, F2 and F3. F1 is the vector 5, 7, F2 is the vector minus 3, 5, and F3 is the vector k minus 3k. So the resultant force is the result of adding those three vectors, and that must equal a mass 3 times by the acceleration, which is the vector a subscript x, 0. Simplifying the left-hand side gives me k plus 2 as the x component and 12 minus 3k as the y component. Simplifying the right-hand side, 3 times, it gives me the vector consisting of 3 times a subscript x, 0. Looking first of all at the y components of this equation, we can see that 12 minus 3k must equal 0, which tells me that k must be 4. If that's the case, then I've now got 2 plus k must equal 3 times 4. So that 6 must equal 3 times a subscript x. So a subscript x must equal 2. So the acceleration of the particle is 2 in the x direction and 0 in the y direction. Our final example, we've got a particle of mass 5 kilograms rests on a smooth horizontal plane. Set of x and y axes is drawn on the table, with the origin being the position of the mass. The three forces F1, F2 and F3 shown in the diagram are acting on the particle. We've first of all got to find the vector form of the force F1, and having found that, we've got to find the acceleration of the particle, giving the answer as a magnitude and a direction. So, starting with the vector form for F1, we need to set up a right-angled triangle for the vector F1. So there I've got my right-angled triangle. Now notice in this right-angled triangle the x movement is to the left, which means it's negative. So F1 is going to be equal to minus PQ, where P is the length of the line and Q is the length of the line in those triangles. We've got P divided by 6 must equal cos 20, so P must be 6 times cos 20, which is 5.638. Q divided by 6 has got to equal sine 20, so I've got Q must equal 6 sine 20, which is 2.052. So I now know that F1 is the vector minus 5.638, 2.052. Newton's second law tells me that the resultant force must equal the mass times the acceleration of the particle. So the resultant force is simply the result of adding the three forces that we've got. So we've got F1 plus F2 plus F3 must equal the mass of the object, which is 5 kilograms, times by the acceleration. So we've now got the vector minus 5.638, 2.052, plus the vector 7, 4, plus the vector 2 minus 5 must equal 5a. Tidying up the left-hand side, that gives me 3.362, 1.052 as the vector for the resultant force must equal 5 times a. Dividing each side by 5 gives me the acceleration is the vector 0.6724, 0.2104. Having got that far, we can now represent the acceleration vector as a component in the x direction of size 0.6724, component in the y direction of 0.2104. And now using Pythagoras on my triangle, I've got the magnitude of the acceleration must be 0.6724 0.24 squared plus 0.2104 squared, all square rooted, which gives me an acceleration of 0.705 meters per second squared. And we can get the angle by saying tan theta must be 0.2104 divided by 0.6724. So that's giving me an angle of 17.4 degrees. So the acceleration has magnitude 0.705 meters per second squared, and the direction of the acceleration makes an angle of 17.4 degrees in an anti-clockwise direction from the positive x-axis. And that concludes our look at the use of vectors in mechanics.